Okay, so according to Coulomb's law, if two charges are kept in some distance, they will get attracted towards each other or they will get repelled towards each other according to the sign or type of the charges. Molika Dotto, I have already told you, no need to give your attendance right now. Don't join the class to only give the attendance. Okay, so when two charges get attracted or repelled, they will get attracted and repelled with some force, right? That force was explained by Coulomb, and that's why this law is called Coulomb's law. That force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. That means when the charges have higher magnitude, the force of attraction or repulsion will be higher, and if the forces have if the charges have lower magnitude, the force will be less, and that force is inversely proportional to the square of the distance between them. So that means when the distance between the two charges increases, the force decreases. As long as the distance is decreasing, the force will increase. So this force is called electrostatic force. The nature of the force will depend upon the sign of the charges. If two charges have similar sign, the force will be repulsion. If they have opposite sign, the force will be attraction. Yes, this is the final formula, F equal to K Q1 Q2 divided by R square, where K is a proportionality constant. The value for K is 9 into 10 to the power 9 Newton meter square divided by Coulomb square. This is the unit, Newton meter square Coulomb square, and the magnitude is 9 into 10 to the power 9. So this is Coulomb's law. So two main point of Coulomb's law is the force of attraction or repulsion of between two charges, two or more charges, depends upon the product of the charge, directly proportional to the product of the charges. Number two, the force is inversely proportional to the square of the distance between them. So this is all about Coulomb's law. Next topic is electric field. So when we know that when we bring two charges near each other, they will get attracted. They may get attracted or repelled, but up to which distance this force of attraction or repulsion can be possible, it is the electric field of the charge. That means the area around a charged particle up to which it can attract and repel another charged particle is called the electric field of that charged particle. Okay, suppose we are taking a positive charge and we are bringing a negative charge near to that positive charge. So when we bring the negative charge near to the positive charge, it will get attracted towards it. But if we take the negative charge far away from that positive charge, it will not get attracted, because the negative charge is not in the electric field area of that positive charge. So the area around a charged particle up to which it can attract or repel another charged particle is called the electric field area of that charged particle. A positive charge or a negative charge is said to be create its field around itself. This space around a charge in which another charged particle experiences a force is said to have electrical field in it. The electric field is a vector quantity, and the direction of the field lines depend on the sign of the source charge. So, electric field is a vector quantity, and it will get the direction of that electric field will depend on the sign of the source charge. Source charge mean we will check the electric field area about that source charge. Source charge can be a positive charge as well as a negative charge, and we will bring a test charge near the source charge to check the electric field area. So that test charge will be always a positive charge. So see, if the source charge is a positive charge and we take the positive test charge near to the source charge, then it will get repelled, since both the charges are positive. So when it gets repelled, the direction of the repulsion force will be outwards, right? And when the source charge is a negative charge, and when we bring the positive test charge near to the negative charge, it will get attracted towards the negative charge. So the direction of that electric field will be inwards. So direction always, it is a vector quantity, and the direction always depends on the sign of the source charge. If the source charge is positive, then the direction will be outwards, and if the source charge is negative, the direction will be inwards. And we always take the test charge as a unit positive charge. Electric field vectors point away from positively charged source and towards negatively charged charge. That is, I have talked about this, that when the source charge is positive, it is inward, and it is outward. When the source charge is negative, it is inwards. Next is electric field intensity. Electric field intensity at a point is defined as the force experienced by a unit positive charge placed at that point. Okay. So I have already explained you that we always take the source charge as we always take the test charge as a unit positive charge, and the source charge can be positive or negative. We will check the electric field area of the source charge by bringing the unit positive test charge near to it, and when we put the unit positive charge in different area of the electric field, it will experience the force in different intensities, right? That is called electric field intensity. When we bring that is charge closer to the source charge, obviously the electric field intensity will be higher. If we bring far, if we put it away from, if we take it away from the source charge, then obviously the intensity will be lower. So the force experienced by that source by that test charge due to the source charge in different point of the electric field is taken as the electric field intensity of that source charge. The electric field intensity at any point is defined as the force experienced by a unit positive charge placed at that point. Therefore, E equal to F divided by Q. Here, Q is the test charge. The smaller unit positive charge, Q is the test charge. Since electric field at any point is the force experienced by the test charge, therefore E equal to F divided by Q. See here, two charges are present. One is the uh, source charge and one is the test charge. We taken the magnitude of the source charge as capital Q, and for the test charge it is smaller q. So we know the value of F according to Coulomb's law, right? According to Coulomb's law, it is Q divided by R square divided by Q. By cancelling out the smaller q's, the final result is E equal to K capital Q divided by R square. So this is the electric field intensity in terms of the test charge, and this is the electric field intensity in terms of the source charge, and the value of K is 9 into 10 to the power 9 Newton meter square divided by Coulomb square. So any questions up to this?
No, ma'am.
You have understood electric field intensity and Coulomb's law, electric field. All of you have understood about these topics. Understood or not?
Understood, ma'am.
Okay. Next topic is electric lines of force. An electric line of force is an imaginary continuous line in an electric field such that tangent to it at any point given the direction of electric force at that point. The direction of line of force is the direction along which a small free positive charge will move along the line. So, when we bring the test charge near to a positive source charge, it will get repelled outwards, right? We take that it get repelled in some imaginary lines. Those lines are called it will get repelled in some imaginary straight lines. Okay, those lines are called electric lines of force. And when we bring it near the negative source charge, it get attracted towards it, right? So when it get attracted, it will get attracted in some imaginary straight lines. So let me show you a picture. All of you can see this picture.
Yes, ma'am.
Yes, ma'am.
Okay. So see here we take the source charge as a positive charge, and if we bring the test charge near to it, it will get repelled like this in some straight lines. Okay, so these are called electric lines of force or electric field lines. and again for the negative source charge it will get attracted like this. So in some straight line, so when we put it here it will get attracted like this. It will not get attracted in any random direction, it always get attracted or repel in some straight lines. So so see here, when you take the negative source charge it is get attracted inwards, so direction will be inward in some straight lines. So these lines are called electric lines of force. For a positive charge the electric lines of force are outwards, and for a negative charge the electric lines of force are inwards. Though these are the directions. Take a screenshot of this picture. Uh, so these are the direction of electric field lines due to a positive source charge, and a direction of uh, electric lines of force due to a negative source charge. So these lines are called electric lines of force or electric field lines. Okay, so these are basically some imaginary continuous line, and direction depend on the sign of the source charge. Okay, these are some properties of electric lines of force or electric field lines. Electric lines of force originate from a positive charge and terminate on a negative charge, because for a say like that, because uh, for the positive source charge the direction is outwards, and for the negative charge downward direction is inwards. So the number of field lines originating or terminating on a charge is proportional to the magnitude of the charge. Okay, if the charge have higher magnitude, the electric field lines will be more. If the charge have lower magnitude, it will have less number of electric field lines. The number of field lines passing through perpendicular area will be proportional to the magnitude of electric field there. Okay, so if any area electric field is higher, then in that area number of field lines will be more. Two or more field lines can never intersect each other, or they cannot have multiple directions. So this is the important point, that two or more field lines can never intersect each other. See, when you see that picture, the field lines are always away from each other. So that means they can never cross one another. If they cross one another, we will have to say that they have multiple directions, which cannot be possible. Uniform field lines, straight, parallel and uniformly formed. Field lines cannot form a loop. Field lines are always straight lines, they are not circular, they cannot form loop. Field lines always flow from higher potential to lower potential. Higher potential means where the near the source charge the potential is higher, and away from the source charge potential is lower. If in a region electric field is absent, there will be no field lines. Obviously, electric field is zero means now there will be no field lines. So this is the end of this chapter electrostatics. In the next class, I am going to start current electricity, and I am expecting more students in that class. So if you have any confusion in today's class, you can ask. Okay, no doubt, students. Give me your attendance one by one. Unmute your microphones and give your attendance.
Ma'am. 044.
Wait. Okay, start giving the attendance.
72.
052
72. Then
052
052. Then
44.
44.
76, ma'am.
19.
76. 19. Then
009.
009.
76, ma'am.
62. Yes, 72 is given. Then
13.
13.
Yes, ma'am.
76, ma'am.
Yeah, 76 is given. 76 is given.
No, ma'am.
What?
4840.
08. 048.
40, ma'am.
40.
40.
Yeah, 40. Okay. Then
62.
15.
15. Then
62.
35.
62 is given. 35. Okay. Then
Ma'am, 2.
002. Okay. And
Yes, ma'am. 55. Ma'am, 67.
055. 067. And
7. 55. 048.
054. It is given.
55.
55 is given.
45.
Okay. 045. And
27, ma'am.
27. Okay. Okay, please tell all of the other students to join in my practical class because I have some important topic to discuss. Thank you.